Let's get started. Today's a special day. We have the Bob Cess Symposium. So we try to have this every year, although we may have skipped last year. There were a couple of things that came up last minute. But anyhow, this day is to honor the late distinguished Professor Emeritus Bob Cess. We do this for many reasons. I mean, Bob is really why we're all here. Because Bob really got atmospheric sciences started at Stony Brook way back in the 70s, initially in mechanical engineering. But right away, he made some huge impacts, and his impacts through the whole climate community are every time I'm out there, people talk about Bob and everything he did in terms of greenhouse forcing papers and model comparison papers, and the list goes on and on. Right. So we're here to honor Bob, and we're going to do this a couple ways, although I'm going to talk in reverse order. We are going to try to have a group photo. We do this on the symposium day. So I'm glad you're here, and everyone's stressed. So, which is fine. We have a hallway of these photos, so you can go back in time and see how some of us have aged. But anyhow, it's the weather, the forecast is looking grim. Rain is coming in, it's windy, so I think we're gonna do it in the Swanson room like we did a couple of years ago. So we're gonna, right before lunch, do that. So just to give you a heads up so you don't bolt out of here, and so forth, and there is lunch, and so forth. So each year we do this, we have a distinguished scientist give a presentation. And so we're very pleased to have Dr. Mark Miller join us from Rutgers, where he's a professor there. Mark is very familiar with this place for a couple of reasons. He taught some courses here many years ago here at Stony Brook, and helping us out in various ways that way. And then Brookhaven Lab for many years. I have a time period 2001, 2007-ish. Where, founder and leader of the Cloud Properties Group there at Brookhaven National Lab. And then over to Rutgers, I believe, after that. And where he, from 2012 to 2023, he served as a director of the New Jersey Department of Environmental Protection Photochemical Assessment Monitoring System, PAMS, at Rutgers. 2023, Mark served as the co-lead scientist for the Eastern Pacific Cloud Aerosol and Precipitation Experiment, FCAPE. So he's highly involved in the field. And so the bottom line is Mark has made many significant contributions in especially marine boundary layer clouds. That's his love and passion. He was trying to convince us last night to go over to the dark side and switch our research programs and study clouds.
I'll try to convince you even more.
But anyhow, so this talk is about that. But before we do that, I want to give Mark, show everyone this beautiful plaque, right? So this is a plaque saying Robert D. Cess Distinguished Chaos Seminar Speaker, Mark Miller, right, from the School of Marine Atmospheric Sciences. And so yeah, we're just going to do a quick photo thing. Yeah, why not? So we're gonna.
Great.
Thank
you, Brian.
So take it away, Mark.
Thought I would start by talking just a little bit about, for just a couple of minutes, about Bob Cess. Pardon me. How did I get to know Bob, and what's my history with him? So when I was a postdoc, or just after I was a postdoc at Brookhaven Lab, I met Bob Cess at a couple of meetings. Generally, I've been in a crowd of people where Bob was talking to someone I knew, for example, and that's pretty much how I knew it. And so one day, I'm sitting in my office, building 318 at Brookhaven National Laboratory. A few people will remember, I use the word office loosely, but phone rings. This is back in the dial phone days. I pick up the phone, and at the end of the phone, it's Bob Cess. First thing I thought is, Bob Cess knows who I am. So Bob says, look, I got some work that I'm working on that I think I'd like to talk to you about. Would you stop over your endeavor and talk to me about it? I did. And he hands me a couple of floppy drives and he said, I think I heard you know something about radars that measure wind. He said, I got these from some Canadian observers and can you make any sense of this? So he hands me the two floppy drives with a binary file code read on there. And I go back to the lab and I managed to read the files and I brought them the results back to Bob a couple days later. And then he says, well, I'd like to help fund you to do some work with me. And I said, well, that's terrific. He said, because there's a few more than just these two floppies. Brings out a box of floppies and says, can you turn this into a wind record? And I said, I will do that. And he funded me for, I guess, 2 or 3 months or something, which for a young scientist is a bonus. 2 or 3 months of funding is really well. So it's really an honor to give a seminar in Bob's honor. And certainly you'll be a little disappointed. I'm probably not going to be talking about clouds specifically and the performance and climate models. However, I will say that back in, I guess, 2012 or 2013, published a couple papers that were right down the lane that he would have really liked. Today, however, I will be talking, if I can get this to move forward, about, let's see, how do I get this to?
You may have to push the arrow on the computer for the first one.
Yeah, it's maybe the. Just.
Oh, that one, I see.
And then it
Now it should.
requires a jump start.
Okay, so today I'm going to be talking about my favorite topic, and I've been studying marine clouds for a very long time, and I'm old enough now that I think I'm able to give a perspective talk on this. So I've titled this "Technology to the Rescue," and I'm going to be talking about how observations and models have actually really changed my view, and I think the view of many others, on exactly how marine boundary layer clouds function. So obviously I have funding for this. There are some known funding agencies here. The Department of Energy over the years, the ASR program, the National Science Foundation is funding work that I'm going to be talking about late in the talk. And this last one might surprise you, the U.S. Coast Guard search and rescue. I will mention something that we've done for them and why it's important in terms of the research that I do later on in the talk. So I'm not going to mention them too much, but I definitely want to tell you that this is a group effort. These are members of my group. They're listed here. Dr. Shushin Zhang, who's been a PhD student of mine and postdoc for a very long period of time, will be leaving me in June after many years, but I want to recognize everybody in the group here. This is a team effort for sure. So I want to start out with this very complicated, crazy looking diagram, which shows why I think I need to talk about advances. So this is a slide that shows, it's a combined slide. The top panel here is all about how much storage space that we currently use in the field for scientific data. And this ranges from where I'm going to be talking about initially here in the early 60s to 1 kilobyte and 1 megabyte up to 10 exabytes. And along this bottom axis here, and even along this line, I've denoted a few things, including, for example, the first ARM site here in the middle. But along the bottom, the things that have really contributed to this. First of all, observing technologies. If you look close, you'll see I have cloud radar in here. A lot of people in this group understand what that is. Modeling advances, climate modeling milestones. And in parallel, of course, there's been a huge advancement in our ability to compute things. And so it is all of those things that I think have contributed to where I believe we currently stand in the field of marine boundary layer clouds. And so I want to start with the beginning. And this is 1968, paper by Lilly, Doug Lilly. Pardon me. So in 1968, Lilly started it all in terms of marine boundary layer clouds. And he wrote a paper which had a very simple slab model. The slab model contained 4 layers. It had a cloud layer, a well-mixed boundary layer, a surface layer. Of course, it had fluxes of sensible and latent heat into the cloud layer. But the key finding was because this boundary layer cloud was overlain by a very warm, dry inversion, that the energy source that actually was able to maintain this boundary layer, and I'm going to show this in a graphic form a little bit, actually was radiative cooling at the top of the cloud. This was, in a sense, the continental boundary layer upside down. Instead of warming, heating, thermals rising, this is cooling at the top and thermals sinking. That was the energy source. In Lilly's paper, he titled this radiatively effective cloud cover, meaning that the net radiative flux at cloud top was the primary source of energy that mixed the marine boundary layer. However, I add the caveat that it isn't the primary source, but we must also remember that the buoyancy flux at the ocean surface is also an important contributor, even though it's not the primary source. Now, what is interesting about Lilly's paper, if you go back and read it, so I said, what did Lilly want us to really understand? So Lilly writes, future investigation. He'd like us to understand why marine stratocumulus, and Lilly was talking about California marine stratocumulus. So this is, I'm going to talk a little bit more about that kind of cloud in a bit. But he was talking about a specifically well-forced single layer cloud system. So Lilly asks, why is it that these clouds don't stay a layer cloud? Why is it towards the tropics they actually evolve into cumulus convection? So that was his first question, was that. And a sub question of that particular thing was, well, if in fact they evolve into cumulus, then he'd like to know why, because this was early satellite photos, why were these big mesoscale elements over the ocean as part of that transition process? Lilly really wanted to know how that worked. Lastly, his plea for an observational study, relatively modest by today's standards. He thought that to solve the problem, he would need a stationary ship for a week to possibly as much as 10 days and an instrumented airplane for a month. Now, probably he was trying to get someone to fund that, which is partly why he put that in there. But I thought it would be a really, really interesting thing now to look back at, well, how have we done? Are we able to say anything about this? Keeping in mind, that was 1968. Now, many people in this room will not know this, but there are a few that will. There are some contributions along the way in marine boundary layer clouds that I kind of need to recognize before I get to the 1995 part here, where I'm going to talk about in a little more detail. So basically in 68, Lilly says it's cloud top radiative cooling. That's what's maintaining the marine boundary layer. In 1978, Stephen Nichols wrote a paper that says, well, that's true, but if the boundary layer gets deep enough, there isn't enough energy from raw radiative cooling to actually maintain the boundary layer. So he introduces the term decoupling, or says that the marine boundary layer can become decoupled from the ocean surface. A couple of years later, in the 1980, a couple of papers in the Journal of the Atmospheric Sciences written by Dave Randall and James Dearorf proclaim that if you want to solve the Lilly question about how you take a single layer cloud and convert that into cumulus, well, that's an instability, a thermodynamic instability at cloud top called cloud top entrainment instability. And that was blamed essentially, or at least I would say hypothesized, as the process that may govern this transition. Wasn't more than about 5 or 6 years later, the way science works, of course, as soon as something comes out, we're all going to kick the tires on it. We want to figure out whether it really works. It wasn't long before we realized that actually cloud top entrainment instability was not the reason why cumulus actually evolved from stratocumulus. It wasn't until the early 90s, in fact, in 1995, Bruce Albrecht actually wrote an article in BAMS describing a big experiment that we had done called Aztecs. And in that experiment, we learned that actually it didn't happen the way Lilly envisioned. Lilly had envisioned a solid cloud layer that developed breaks. and became cumulus. That the breaks actually then allow these little clumps to actually become cumulus, and that's how the transition worked. But in fact, that's not how the transition works. In fact, what happens is the stratocumulus actually develops, and then underneath it, cumulus develop for reasons I'm going to talk about in a little bit later. So there is a hybrid cloud type in the middle there. All right. That was in 1995. Early research on the transition. How did Lilly perceive this transition? Well, it wasn't exactly right. In 1995, we're starting to figure out how it actually did happen. Then I have this break, okay? And it was that. And I think it was partly funding, but I really think the reason was in 1995, we had reached the edge in what we could do. We had new instruments, but they were just prototypes. They really weren't very good. They were getting better. And modeling, LAS, Murat, I see is in the back, was around, but wouldn't you say that at that time, LAS was still really hard to analyze? It was very hard because the computational power wasn't really there. And while we could run mesoscale models at fairly decent resolution, computer power really didn't exist to do very large scale simulations, especially over the marine boundary layer that could move this problem a little bit further. So it kind of festered, at least for a while. Now, I want to talk about back in the very first request that Lilly made. He wanted to know a little bit more about California stratus, right? And the Nichols paper in I guess it was 10 years later after I think it was 78, Nichols wrote the paper on decoupling. Well, I want to talk just a little bit in very basic terms about the diurnal cycle of marine stratocumulus. And I don't think my animation is corrected here. It doesn't seem to, or at least let me try to get the animation to work. Not working the way it should. But at any rate, let me talk you through it. So take away the sun here for a moment. At night, we have IR cooling, thick layer of stratocumulus, probably drizzling, lots of IR cooling, yet no sunlight here, even though the animation isn't working correctly. So the boundary layer is very energetic and mixed very well by the radiative effective structure at cloud top that Lilly outlined. When the sun comes up, vapor in the top of the cloud begins to absorb some of that radiation and heats and offsets some of the cooling. And as a result of that, the energetics are broken because now there isn't enough energy combined with the buoyant energy at the ocean surface that's helping the updrafts here. You can think of this as the cooling is driving negatively buoyant parcels down to the surface, and there's a little buoyant energy here that's actually helping them rise a bit. But as soon as we bring the sun into the picture, that energy balance is broken. All right. There isn't really enough energy to maintain the entire boundary layer. And so even though I have a dashed line here, it's not really a hard line. But what happens is because we have reduced this energy, we now aren't able to completely mix the boundary layer. And so a separate internal boundary layer develops down near the ocean surface. It's not really a strict line. There is still some exchange, but it is essentially a line that allows vapor and aerosols to now begin to accumulate down near the surface. And when that happens, of course, now we don't have any supply of vapor to the cloud. So during the daytime, vapor and aerosols down near the surface are captured, and the cloud has no source of vapor, and therefore it thins and somewhat evaporates. So this was Lilly's view of the simple slab California stratus layer and how it actually evolved. But we really didn't have, in all of those years, there was really only one experiment that had a very extensive amount of data from California stratus that could have been used possibly to look at Lilly's thoughts on this and how the stratus system worked. But that was kind of an inadequate experiment because it was conducted long before we had really complex instruments like we have today. So along comes the Upcape project in February 2023. I worked with Lynn Russell and Dan Lubin at Scripps on this, but the experiment was conducted under the auspices of Lynn Russell at Scripps. This is the La Jolla, California Scripps Pier. There's some stratocumulus there. There are a bunch of instruments out there. These are complicated instruments, the ARM mobile facility, that are meant to then measure the structure of the clouds above over a very long period of time, something Lilly had asked to do with a ship over a few days. We now have a year of this. And from that year, Brenda Gate, who's worked with me at Rutgers and is at Argonne National Laboratory now, does a lot of work on marine boundary layer clouds. Finally, after all that time, here it is. Lilly's California stratus, basically the climatology of the diurnal cycle. And this is a year of data where every time we had stratocumulus in there, layered stratocumulus, Brenda consolidated all of that. And what we can show is that just as our thought process and that slab model showed, basically we have a layer of cloud here. Let me get you oriented here. This is 24-hour period here. This is boundary layer height. Notice that the boundary layer depth here is about 700 meters. So this is not a very deep boundary layer, just like the one that Lilly envisioned. So now, basically, we have a thickening cloud layer at night. And that's part of Lilly's model as well. Notice the blue coloring here, which is a radar, cloud radar, which is telling us where hydrometeor echoes are. And we'll see the subcloud layer here, this thick drizzling stratus, drizzling because we know that when stratus becomes fairly thick for reasons, if it's beyond about 100 grams per meter squared, it's sort of an empirical number, it will drizzle. And so it's drizzling at night, but when we have sunlight involved in the process, you see quickly cloud bases here. These are statistics of cloud base. When that sun comes up and the boundary layer decouples, then at that point, we start to see a thinning of the cloud, and that's indicated down here on the bottom panel here. This is the liquid water path in these clouds. This is the 24-hour cycle. You can clearly see that as the sun comes up, the boundary layer decouples. We get the diurnal cycle that Lilly envisioned. So I think Lilly would probably be approving of this, but we went a little bit further. So we also know something that Lilly didn't account for that we learned later and knew later, which was that marine stratocumulus tend to be very microphysical beasts, and they are sensitive to microphysical processes, to microphysical structure. So we're trying to understand how a basic cloud type like the one that we see off California might actually respond to aerosols. And so the other part of the Upcape experiment was basically an instrumented laboratory that was set on a hill, Mount Soledad. It was called La Jolla. Down there is the Scripps Pier. Whenever there were stratocumulus that moved in, 700 hours of the time that we did Upcape, we actually had observations of the aerosol inside the cloud and the cloud droplet structure. And from that, we published a paper just recently, actually, that shows that we can now characterize the post-cloud, pre-cloud, and in-cloud aerosol structure. We've known for a while that marine clouds process aerosols over time. And I'm not going to talk in detail about this, just to tell you that this bimodal structure that we see outside, this little void right here is a hysteresis in the cloud system. And what it tells us basically is that when during this cloud's evolution was the updraft the strongest and the supersaturation the greatest, something we call the Hopple minimum. The point here is, in a perspective talk like this, I just want you to know we're getting somewhere in understanding how the evolution of not only the cloud works, but also its internal microphysics, at least in this simple cloud system. But what about the rest of the world's stratocumulus decks? And there are an awful lot of them. So this is sort of a classic figure that Rob Wood published back in 2012. It shows basically annual cloud cover from stratocumulus clouds. We're going to focus over the ocean here. And right away, you're taken by the fact that there are places around where annually the cloud fractional coverage is 60%. So very, very cloudy places around the planet. These are marine boundary layer clouds. And there are certain regions, we've known about these for a while. One, of course, is the California region that Lily was envisioning here. But there are other regions that are very similar, all involve very cold upwelling ocean water, and then a subsidence inversion, which sort of caps the boundary layer with this very cool ocean cooling it from below. Very heavily forced on both the top and the bottom in these regions. Now, the yellow X there at the top is an area in the eastern North Atlantic. That's a little different type of marine stratus than the stratocumulus that occurs along the California coast. The stuff along the California coast, very shallow, very sharply bounded by a very strong inversion at the bottom top and very cold water from below, forced heavily. Here we have an area of stratocumulus that actually is a little deeper. The boundary layer is deeper. It isn't as heavily forced by cool ocean water from below, and it has a little bit more variability in the subsidence rate that caps the boundary. So this is a bit deeper boundary layer and a different kind of stratocumulus, but it starts to address Lily's question about what happens when you move equatorward of an area that has strong stratocumulus coverage. This also happens off California and these other regions. You'll see gradients in here. Lily would have been happy with some of the results that we have now about that particular area. So we've learned a lot over the years about how that transition process happens from single layer stratus to cumulus. I'm going to walk you through how this happens. If you understand decoupling from that previous slide, that is energy supply at the top, then I can walk you through how we can convert stratus to cumulus through a hybrid stage. All right. So here we have the classic Lily stratus, a little bit deeper boundary layer. Those of you who recognize the lifting condensation level will know that if it's right at cloud base, that means that there's a connection between the surface, the sea surface temperature, and cloud base. I mean, this is a well-mixed boundary. They're totally connected. All right. So now let's move a little bit to a warmer sea surface temperature, and let's reduce a bit the subsidence rate at the top, as if we're moving in the Hadley circulation down towards the equator. All right. So in that case, the boundary layer deepens because we lessen the subsidence rate, and we also change the sea surface temperature. What happens then is when we deepen the boundary layer, now we've upset the energetics up there. So we don't have enough energy at all to mix the boundary layer, but when this first begins, the lifting condensation level is still found up in this drier area. So we still have this thin stratocumulus deck, but the lifting condensation level will not allow vapor and aerosols, and most importantly, the convective available potential energy, which has now risen in the subcloud near the ocean layer here, to be realized, because the LCL is just above that layer. But a little bit more time goes by, we accumulate a little bit more vapor, get a little bit more temperature change here. Suddenly the LCL arrives down in that lower layer. This is a conditionally unstable environment. So as a result, cumulus clouds will form. So when they form, they now reinvigorate the stratocumulus. So what was a dying cloud is now a new cloud, one that has been supplied now by cumulus convection from below. This is the classic Albrecht 95 transition structure. This was modeled by others. I'm giving Bruce credit, but there are a lot of people who have a lot of credit in terms of figuring this particular process out. Eventually, of course, as we reduce the subsidence rate even further, we increase the buoyancy flux of late heat fluxes and warmer ocean water. Eventually, the stratocumulus just can no longer exist, and it goes away. All right. So that's sort of the conceptual answer to Lily's question. The problem lies right here. So when you look at models, And one good model that we all use, a lot of us use, is ERA5 as a reanalysis. So it's part model, part data reanalysis. When you look at that model and you have observations, as we do, a lot of them, from various regions. We wrote a paper a couple of years ago, 3 or 4 years ago, my postdoc and I wrote a paper about this, in which we were able to show that ERA5 does a really nice job if you have single layer stratus. And it does a really nice job if you have individual cumulus elements. If you have a hybrid cloud structure like that, it's terrible. It does a really bad job. ERA and a lot of models suffer from this, do not handle the decoupling process very well. So what are we going to do about it? Well, now it's time to take a look at the next step here is what are we learning now? And now we're in a position where we have very sophisticated instrumentation. There is the Eastern North Atlantic arm site. Many of you have probably seen this picture, some have not. It's equipped with everything, including very sophisticated cloud radars, pretty much everything you'd ever want in a field site. Very well developed instrumentation, very well tested and well known. So we have this on Graciosa Island off the coast of Portugal. Okay, there's the island there, and there's a site on the north side of that island. And from that site, we have gathered data for a period of years, right? And we're going to look now at what we're learning about that hybrid cloud type, cumulus rising into stratocumulus, because that's the one the models struggle with. Part of the problem is that those are mesoscale beasts. They become organized on the mesoscale, right? Mesoscale is not parameterized well in climate models or low resolution models, nor is the vertical resolution in those models sufficient to pick up decoupling very well. So we need to learn a little bit more about this beastly cloud type. So here are some pictures, and I'm going to show you one thing that we didn't know until a couple of years ago. In fact, we're just publishing this now, hopefully. We didn't know what the scales were. Didn't even know what the basic size distribution looked like. No idea. Well, I guess we had some idea from earlier experiments, but here's an example of how we did this. We basically had years of data. This is summertime. I'm going to focus on summertime marine stratus. Sun angle's a little higher. They're a little more important at that time of the year in this area radiatively. So here's an example of where we've taken these structures, we do a time-space conversion with the wind to figure out their scale. Here's an example where on this very fortuitous day over a 4-year period during the summer, we happen to find all 3 scales in one day. So let's just figure out what the statistics are. I mean, if they're mesoscale, well, how bad is it? And why I say how bad is it? Because we really kind of need, if we need to resolve these in a model, we kind of need to know what scales we need to be thinking about here to resolve this. All right, so here are the summertime statistics here. Anything less than 20 of this black bar, and then 20 to 50 kilometers. These are the numbers and percentages of structures that we observed during those 4-year period. You'll notice that the vast majority, roughly half of them, are less than 20 kilometers, which means we're going to need to resolve those with a model that's on that scale, less than 20 kilometers. And at 20 to 50, 33% we might be able to resolve if we had the right model on this, at least a large scale model. But 80% of these structures are less than 50 kilometers, and a very large proportion of them are not going to be resolvable even in the best medium range or climate model right now. So I want to turn the clock back and show you that I'm going to try to understand what's the difference between those two most predominant scales. Those larger scales are a little more frontal. There's a lot more stuff going on. I'm not going to worry about those. They aren't a high enough percentage right now. We just like to figure out how one of these things works. So this is a paper we published back in 1995, and I want to point to this because this is a structure. This is like a hieroglyphic compared to what you just saw now. This was a state of the art of 95. This was like, wow, we've got clouds in radar. So, and this is drizzling stratocumulus here. Not going to get into all the details. This is the equivalent potential temperature trace at the surface during the passage of this structure. All right. And you'll see that this hieroglyphic looking graph shows a dip in the equivalent potential temperature as this thing passes. All right. Symptom of an exchange. Since theta E is a conservative variable, even in drizzle, this is going to basically be a symptom of a mixing that's occurring through the boundary. Is this a downdraft driven cold? What is this? Okay. Now you'll notice that over here on the right, I have a plot here that has delta theta equals 0. So when it turns out that we had a grand total, a massive total of 5 observations of this. Okay. So this total, delta theta equals 0, means that when this thing passed, there was absolutely no signature at the surface. That lack of a signature at the surface tells me that when that cloud was drizzling, that drizzle was enough to moisten the air below, stabilize it a little bit, but it wasn't enough to actually cause an evaporatively negatively buoyant driven parcel to go all the way to the surface. All right. Whereas of our 7 structures, structures A and H were capable of producing a downdraft that was observable at the surface. So this has been somewhat unexplained for a long period of time because we just didn't have the statistics or the models to do it. Now we do. I'm not going to explain it totally, but let's take a look at what we could do. If we had those structures that I just showed you, several hundred, and we happen to launch soundings in a whole bunch of those things, all right, then we would also have an average profile of the equivalent potential temperature. And then if we, every time one of those things passed, we took a big computer program, which my student Stephanie did, and we analyzed that little dip and we measured it. We said, well, how much of a dip is that? When was the latest sounding? So this is the perturbation at the surface. And we did that a whole bunch of times. Then we could contrive a little equation right here that would basically tell us, if I saw this perturbation, where do I think that came from in the profile? How high up in the boundary layer did that come from? The attempt here to explain that one, the observation I just showed you, that some of these structures don't produce a downdraft and some do. All right. So the question is why? All right. So given that I can do this mixing depth exercise, now I'm going to talk you through a graph. Okay. 2 graphs, actually. I'm going to point out some features of this, and then I'm going to show you a comparison of these 2 plots with the 2 scales, which I think will provide at least a little bit of an answer as to why we saw 2 different types of structure. All right, back in 1995. So this is the complicating plot that I'm going to show for both scales in a bit. But there's the basic, for every sounding that we had in any of these scales, we took the average potential temperature. We defined the inversion. I won't get into how we did that, but we did. And if I know the temperature profile and the pressure, I can calculate the saturated equivalent potential temperature. So if the sounding goes up in a cloud, theta E is going to equal theta ES, the saturated equivalent potential temperature. So if I know the mean profile and I know the saturation profile and I happen to know how many times I was in a cloud and how many times I wasn't, well, then I can retrieve, if I have some information from cloud radar to tell me when I was in cloud and when I wasn't, then I can actually subtract when I was in cloud from the total profile, and I can figure out how much, what the unsaturated profile had to look like, hypothetically. And this is a lot of data. So what I see here is this, you can see that I've got some layering in the unsaturated part, even though the total profile looks fairly, and I'm going to show this in a bit of perspective in a moment. So the other thing you can do, oh, by the way, I forgot to mention this. This is a calculation using that surface perturbation that I was talking about of the mixing depth in this particular case. And then over here, I just plot the blue is really the profile of merit, which is the wind speed. And I'm not going to get into this much, but the wind speed divided by 10 is plotted here. I'm just going to show you one aspect of that. But now let's compare the profiles from the two scales here. All right. Let's give you a second to look at this before I blare off into what it all means. So here we have on the left-hand column 5 to 20. Here we have on the right-hand column 20 to 50. Again, unsaturated environment. If you were inside the cloud, total profile cloud radar statistics, wind speed. All right. So what do we see? Well, there's a big difference here. The first is that in these smaller structures, the environment is stratified. It's decoupled, very stratified and layered. Right? Got a moist layer at the top, but you can clearly see that there's a difference between the area near cloud top, the area near cloud base. You would agree with me, the unsaturated air around this structure is stratified. Right? On the other hand, if I look at the larger structures, I don't see that. I actually see what looks like a well-mixed boundary, which is a little confusing to me. It was definitely, still remains a little confusing to me. So this is the big one. When I do the mixing depth calculation using two different techniques, the one I showed you and a slightly different one, because I didn't believe just one. When I look at the smaller scale structures, the air that's coming down to the surface is coming from just above your head. A couple meters, few meters, tens of meters. Whereas both techniques in the larger structures clearly lie right on the lifting condensation. Meaning that air is basically evaporatively coming downward from cloud base, and that is what's causing that perturbation at the surface. So the downdrafts are really interesting here and may explain that early 1995 experiment. Basically, the environment, the downdrafts exist primarily in the larger structures that actually get down to the surface. Smaller ones don't have as much of it. Now, and by the way, wind speed is much larger, actually about double when you have the larger scale structures. So wind is not insignificant. Now, I'm going to kind of go into another part of the talk here. So great, thank you very much for all those observations, but now let's pull out the model and see what the model says. All right. I'm interested in the smallest scale. I want to know just a very basic question. What does it look like in the model? All right. So we pull out an entire simulation of the Eastern North Atlantic on the Duratio computer out at NCAR with 1.3 kilometer horizontal resolution, 15-meter resolution in the vertical, which may or may not be enough, as I talked to someone here today. But at any rate, we picked out one of these structures. I did say, well, let's just follow it. These X's are sort of its Lagrangian pathways. And then right about here, I said, what does it look like now? And I have plots all the way around. Let's look at it here. This is, of course, Latin lawn. This is just cloud fraction. These are these structures in the model. You know, after a cold outbreak, the transition type of structures are right here. So let's take a look at one. By the way, we found out that these in the model believes these go through an expansion contraction cycle on a period of about 20 or 30 minutes. So it expands, grows up, and it collapses. Grows up, and it collapses. Well, let's take a cross section through it and look at the equivalent potential temperature, which is a conservative variable. All right. So we're going to look at that conservative variable at three places: right at cloud top, at the cloud base, and in the subcloud midpoint. The arrows here are relative wind. So I've taken the wind vector, the average wind vector, and subtracted that because I want to see what the flow is relative to this thing. All right. So here's the cloud top, cloud base, mid cloud, subcloud. And then the contours here are divergence. If it's in red, it's convergence. All right. So what we see immediately, let me just move forward. In the interest of time, I have to kind of remind myself what I want to say. So we clearly see at the cloud top, as expected, theta E is telling us that we're connected almost directly to the surface. So through this thing, we're getting air from the surface right up to the inversion at cloud top. Notice also these blue circles here, which are divergence, telling us this is a multicellular structure. It's not just one updraft. In the model's view, this is more than one updraft, and they're somehow collaborating. What I don't show here is that the biggest updrafts, and a big surprise for me, I expected to find the biggest updrafts at cloud-based, but that is actually not what the model tells us. Model tells us the biggest updrafts and downdrafts are actually at cloud top. Surprised. Don't know whether it's real or not. It's what the model says. So at cloud base, we see convergence. Oddly enough, just talking to a couple of students about severe storms, and I guess it was me talking about the analogies here, see a rotational component in the relative winds. Okay, so it's got a lot of vorticity. There's a lot of convergence right at cloud base. But that last one there, cold pool, there it is. The model says there's some sort of cold pool sort of impinging on this structure. And right here sort of outlines that cold pool. Okay, so the model is saying, yeah, there's a cold pool. But does the model answer the question of whether, since this is a 5 to 20 kilometer structure, which shouldn't have a downdraft, which reaches all the way to the ground, according to the observations and the analysis from those observations, guess what? We see convergence, no well-defined cold pool. So in these smaller structures, it appears as if the evaporatively driven downdraft may not have enough oomph when it reaches near the subcloud layer. There just may not be enough. It may be too moist to get enough evaporation to actually let it go all the way down to the surface. It's still too moist. Maybe there hasn't been enough vapor evacuated from the boundary layer in these smaller scale structures. But this to me helps explain why we don't see a cold pool, even though we do see a small divergence signature. We see some mass movement, but we don't see the temperature and vapor gradient that we see clearly that matches that and cloud tops suggesting there's a connection. Last thing I'm going to show, and I'm almost done here. I've got to finish up in about 5 minutes. This is going to be really quick. So we wanted to analyze basically the top here is just us sorting out all the clouds around a main structure. This is the cloud base, cloud top, and then determining that area. I don't have time to talk about it, but I'm just going to show you. I spoke to somebody in the meeting. This is the model I was talking about. So this is a mass flux model, a very simple one that's based on something we saw in the observations, that there is no change in relative humidity depending on no matter what scale, the relative humidity underneath these things stays locked, no matter what's going on. So you can develop a mass model, mass flux model, and you can actually successfully get at the contraction phase. We haven't really figured out how to get to the development phase, but I just wanted to show you that there is hope and then talk about what we're doing now. All right. So this is some work that I'm doing with Christine Chu and Peter Van Leeuwen and my PhD student, Stephanie Braddock, and another PhD student, Juhan Su at Colorado State, in which we're now going to try to figure out why. So our question is, what is driving the cloud fraction in the model? What is it? We're resolving the biggest convective elements. So the idea here is that we're going to use a technique called causal analysis. Okay, this technique is a statistical analysis that basically allows us to identify one variable, cloud fraction, and then identify a series of associated variables and decide which one of those associated variables is most important at a given time period in the evolution here in determining the main variable, which in our case is cloud fraction. In order to do that, we had to run 10,000 trajectories through FlexPart. I don't have time to talk about all this. This is work in progress. I just want you to know what we're doing. So when we do 10,000 trajectories, this is the Eastern North Atlantic site, Here's a similar case to the one I just showed you. So these trajectories are spreading out. We can take those trajectories, and some don't have clouds, some do. So we can start to remove those. We can then start to do things like map the geometric cloud thickness. And if you look close here, you'll see that some of these trajectories down here start to develop cumulus. Those structures we're talking about. So that evolution is in these trajectories. Now, I don't have time really to, I'll just show you on the bottom that we also analyze some of the variables that go into that. These are some of the causal variables that we're using, not an extensive list, but we record the latent heat flux and near surface wind speed and basically the vapor gradient near the surface in the model. The idea here is we want to learn what is modulating the cloud fraction, because that is still very deficient in not only the model that we're running, but essentially all models that I know of that try to do marine stratigraphy. So that's the way that's the way forward here for us. I want to show you that in our simulations, we get all kinds of different clouds along trajectories. I had a couple laid out there. One trajectory doesn't really have much cloud until all of a sudden, down near the end of its life, one of these structures that I'm talking about develops. Other times we have trajectories that have nice layered stratocumulus that kind of rises and then disappears, sort of a lily-like fashion in a way, and then multi-level layer clouds downstream. The object here is that we have all these 10,000 trajectories, which when I was told by Peter Van Leeuwen I needed 10,000 trajectories, I nearly had a heart attack, but that's what we did. And I think we're going to be able to actually address that because we have a rich enough variety of clouds here to actually get at some of the physical processes that might really be driving the cloud fraction in the model. Now, whether that really works in real world, we'll have to figure it out. The last thing I want to show is something that that we've been doing that's completely in a way unrelated to what we've been talking about. It's the last slide that I have. It is about some development that we've done in support of the U.S. Coast Guard search and rescue operations. I talked to some of the students about this particular work. This is where the Coast Guard asked us, we have a high resolution coupled ocean atmosphere model that we developed at Rutgers. So we have 1 kilometer resolution wharf model that's affixed to a 1 kilometer implementation of the ROMS model, the ocean model, and we have a coupler that we can do one-way or two-way coupling. So, and what was the Coast Guard's question? Well, the Coast Guard wanted to know if you fall in the water on the downstream side of a wind turbine, has enough cold water been kicked up that it might affect your survivability? Or if you're flying a helicopter around one of these things, what kind of wind field might you expect? Now, I won't talk about the results here, but I will talk about the future. So this model can be used. Now, I won't kid you, when I heard about this project, the very first thing that I thought was this is a good amount of money to develop the model I need to study marine stratigraphy. So yes, I'm in with turbines in this model, because as soon as this work is completed, which will be about a month, this model is getting taken elsewhere, and we're going to be studying clouds. Now, we may or may not do we may do some work before we do the coupled version of this for Eastern North Atlantic, but I'm just saying you this, or just telling you this is a model which actually will allow some exchange between the ocean and the atmosphere on fairly short time scales. I want to finish it right on, I guess, right on time. Brian might be happy with this, but I've got one slide left. I think Lily would be happy. We made progress. He wanted one, a ship observation and a feeble amount of aircraft time. I think we've done that many times over in FK, plus a lot more sophisticated approach to things there. Measurement world. In the mesoscale organization, since the days of Lilly, we now understand that cloud top entrainment instability does not actually drive that transition, that there is that hybrid version of cumulus rising into stratocumulus, and it is that hybrid cloud type that is the source of consternation for investigators and for models. We need to understand that a little bit better. I think we do. We now have some idea of the scales and how, which ones or how many might be represented in models of what resolution. We also have some sort of answer to the idea of whether there are downdrafts and cold pools in all these structures, how that fits into the observation paradigm that we're using. I think the answer to that is depends on the scale. You want to see a cold pool, you need to look at a structure that's 20 or to 50 kilometers and you're going to see it. You look closer than that, it'll never make it to the surface. You're not going to see it. We now think, at least in the model world, that actually observations, these are multicellular beasts. They don't have a single updraft. And we find that we can do a fairly good job with an analytic model that just tries to get at the growth phase, traction phase, in this case, the contraction phase. So we'd like to basically do a couple model. I'm not sure whether we'll do it over the Eastern North Atlantic or try it in another area, but we'll do that as our future study. We're going to continue to work on trying to understand what is modulating the cloud fraction in models, basically. And then the last thing I said here is, well, I can't close this without mentioning Bob Cess's favorite topic. I mean, Bob would not be happy if I finished this without telling you that this is one of the biggest and hardest cloud feedback problems there is. And if you look at forward climate projections and you read the IPCC report, you'll quickly determine that it is this type of research, I think, that's going to have to be done in more and more and more detail to get at that cloud feedback question that Bob was so interested in. I think we're all interested in now. So if I haven't gotten you enlightened into the marine stratocumulus world, I'd be happy to indoctrinate you in any way that I can. And if you have questions, there it is.
We have time for a few questions, Ernie.
Mark, very good talk. I really enjoyed it. You've been trying to explain that to me for 30 years, and I think I'm
I'm trying to explain it to myself for 50 years.
So between the let's just say 5 kilometer and 250 kilometer clouds, there was a factor of 2 difference in wind speed, which I found striking. Is that a driver of whether it's a small scale or big scale, or is that a result? Because I could easily see that being a driver. Why?
I believe you are right. It is a driver. And I did not show this, but we have a companion paper. So we have a set of papers that are in review right now. We have part 1 and part 2. If you're a reviewer on it, I hope you enjoyed it. At any rate, the part 1 of that does show a very comprehensive analysis of wind-driven changes.
Yes.
And in fact, we do believe the 2 factors, we believe wind is a big factor in determining the scale. Yes.
Yeah. Yeah.
And I think that's shown even further when you get to the even larger scales. It's definitely related to the mean wind velocity. So the answer to your question is yes. I just didn't show that off.
Questions? Yeah.
Yes, so Mark, for the trajectories you showed that these, as I understand, are from the models. Do you have any observations to constrain the results?
That's a great question. So I showed the trajectories here for one point, but in the work that we're doing, they have 2 elements of it. One is we're just looking at the analysis, the causal analysis of those 10,000 trajectories in the model framework. The other is I have extracted the information on that simulation from the ENA site. So the other element of this is we're running the same causal analysis, but on the clouds that the model produced over ENA. The idea is we want to find out, even though your point is a really good one, how do you possibly verify this unless you did? You may remember this, but probably many people in the room won't. But during Aztecs, we actually did a neutrally buoyant balloon experiment. I don't know if you remember that, but we launched a neutrally buoyant balloon and followed that balloon with aircraft for a period of 3 days, sampling marine stratocumulus in various stages along the way. Something like that is about the only way I could see that that we could validate the trajectory parts. I think our hope at doing the Euleri problem here at ENA really has to do with whether we can convince ourselves the model is actually close enough to reality to believe it. I guess that's always been the question for me. So the answer is I can't validate the trajectories, But I might be able to give myself a little confidence by looking at the Eulerian framework, doing a similar causal analysis on that, this time with observations rather than a model.
Thank you.
Yeah, last question, or how many questions we got? Daniel, we're good. So then,
Mark, great talk. I could really nicely follow your thoughts. As an aerosol person, and clouds form from aerosol, we showed only one aerosol slide. I need to ask that, or I mean,
It's already complicated enough.
yeah, I know. That's why I throw that now in, but it doesn't. It looks to me you're not limited with the aerosol particles, or that is not a limiting case. Let me finish one thought. If you have the downdraft, I guess droplets evaporate. You re-invocate the aerosol, so you have almost a sustained cycle. You could even get better CCN, or if they scavenge other aerosol and then collecting cloud droplets, evaporate.
This is almost the EPCATE study.
Okay,
Because we're very interested now. I can't get on ENA, and I will say, opinion wise, these things are so dynamically strong that I think we wouldn't be able to see it if it was there. I do think in the EPCATE case, we will.
okay.
I think it's partly data constrained. In the EPCATE case, we see evidence of that. We do see evidence. We have, that Dedrick stuff. You remember the Hubble minimum in there. That Hubble minimum didn't get there by accident. It got there because those clouds are processing aerosols. They're moving aerosols from the Aitken into the accumulation mode. And in the process of that, they are creating that void, the Hubble minimum. I think we can study that problem. And I think that
powerful
problem
data set.
it's better studied, I think, with EPCATE. Is it important here? I don't even know. I don't know. I don't know. But I would say I don't dismiss anything when it comes to marine stratocumulus. If you told me that, someone, fishing and seagulls had somehow affected this cloud structure for a while, I'd probably believe you until I was able to convince myself I loved it. So there you go.
yeah, Vince, was there a question?
Hi, yeah, thanks. Fascinating talk. I'm curious with the stratocumulus to cumulus transition, the processes on the buoyancy production, how it goes from radiatively cooling with maybe a bit of surface pulsing, optics. Whenever it's transitioning to the cumulus, have you studied? Is there any evidence to suggest that it's a transition towards evaporative cooling, either in cloud or precipitation?
Well, there's a bit of a different, I should have mentioned this perhaps, because back in 1995, 2D models basically, the buoyancy flux, essentially when you start to get these cumulus clouds, that buoyancy flux, that heat release, if you will, is so strong that it kind of overwhelms a lot of the other processes in the boundary layer. Now, in the downdraft part of things, I think one of the things that I'm really curious about, and this is work that goes beyond the trajectory part of it. I think your point was, do I know what's driving that evaporative downdraft? And I think the answer is I would really like to know that answer. And I think the model has a very good chance of at least giving some insight on that. However, I will preface that by saying I was a bit discouraged in one aspect of the model, which was that it really doesn't produce very much precipitation, which I don't know quite yet how to interpret that, because certainly the structures that I'm measuring do. So how that plays into it, I guess the answer is thank you for that question. I'll be back in 2 years to try to answer that, hopefully before I retire. But I'm not so sure the way things are moving now in terms of the speed in which we're able to do things. Thank you. I think I'll try to figure that out.
No, you'll be back soon.
I'll come back.
Let's thank Mark again.